Welcome back everyone to another exciting video on weather radar. And this is our final video on the radar equation. Where we left off with the radar equation last video, we were looking at the scattering that comes back from a volume of cloud. And we tried to estimate the size or the volume of cloud using the pulse length and also the width and the height of the radar beam. Also the distance the radar beam is from the radar itself. And then we also looked at the number of particles, and we estimated, and we tried to estimate the number of particles by measuring their diameter raised to the 6th power. Also, we said that since this is Rayleigh scattering, we've got to use the equation that deals with Rayleigh scattering, and that has an index of refraction. We said that we really don't know what the cloud is made of, if it's ice crystals or water droplets or a mix. So we're going to assume that it's all water and use the index of refraction for water, keeping that in mind whenever we look at our values for the radar. So based on that, we're going to take the equation for backscatter cross-section area for the Rayleigh scattering regime, put that into our big, mean, nasty radar equation, and this is what we have. So the power received by the radar is a function of a whole mess of things. It depends upon the size of the beam and the wavelength and the gain of the antenna and the power that was transmitted and the distance from the radar. And then this other thing, which is sigma. We're summing sigma, and in this case what that is, that has pi in it, of course. You see pi there. Also you see the index of refraction, which is k raised to 2. It's got the wavelength, lambda to the 4th, but then it's got d6, and that d raised to the 6th power is the diameter of all of those ice crystals and raindrops in that volume of radar beam. So we're going to stick that in there. We're going to start canceling things out. The equation looks really nasty, but we're not going to make any calculations with that. That's all done by the radar. And step back and take a look at that and think, well, what do we know in this equation? Well, you know what pi is. Pi is tasty. And then PT is your transmitted power, how much power the radar is transmitting. G is the gain of the radar, G raised to the 2nd power. Phi and theta are the radar beam. H is the pulse length. So in other words, you know a lot of the stuff that's in this equation. A lot of this depends upon the radar itself. But this D6, that's the D raised to the 6th power. That D is the diameter of each hydrometeor in the radar volume. So what we're going to do is we're going to fudge a little bit, and we're going to call that sigma d raised to the 6th power. We're going to call that z. And that'll be our radar reflectivity factor. And it determines the scattering that the radar, all the cloud does, and all the power that comes back to the radar. So everything in the red box on the top equation is things that are constant for the radar, things that we know. We're going to call that the radar constant. And then we know other things. We measure the power that's coming back to the radar. That's PR. That's what the radar tells us. It tells us how much power is coming back. C is the radar constant, depends upon the radar itself and the wavelength and the pulse length and things like that. R squared in the bottom is the radius, or in other words, the distance out to the radar, and we can measure that with a timer if we know the speed of light. So what we don't know is the d raised to the 6th power, or that z. We don't know that z. So that's our equation. That's the simplified radar equation, combining everything with the radar and putting that into C. So what we're going to do now is solve for z, just using a little bit of algebra, bringing z on the other side and PER, putting it in the bottom there. And this is, we just solved for the radar reflectivity factor, and actually this is what we plot on PPIs and RHIs and other things. It's got units of millimeters to the 6th power per millimeter cubed. That millimeter cubed is the volume of the radar beam. and the millimeter sixth is the reflectivity, of each drop summed. So if we can measure the power, that comes back to the radar, and we know how far out the target is, and we know the characteristics of the radar, we calculate Z, and Z is our radar reflectivity factor. And you've probably heard of Z before. The radar reflectivity factor depends upon, of course, how well the target intercepts and scatters radar energy back to the radar. And it also depends upon the size, shape, and the dielectric properties of the target. In other words, of the raindrops or ice crystals or things like that. Radar reflectivity factor is a huge number. You think about it, it's the diameter of ice crystals raised to the 6th power, and then sum all of those up for the thousands and thousands of ice crystals that are in water droplets or that are in a cloud. So it tends to be a really big number, and it's hard to handle a big number like that, Z. So instead what we do is we use decibels, and decibels are a pretty handy mathematical trick. We use those for power transmitted and power returned. You know that the power transmitted by radar is typically about 1 megawatt from a National Weather Service WSR 88D. And the power that comes back is much, much smaller. It's in the order of 2 times 10 to the minus 14 watts. So we're looking at really big and really small numbers, and likewise radar reflectivity. A radar reflectivity factor is a really big number. So we like to handle that also using dBz. So there's the equation for it. What we'll do is we'll take Z divided by 1 millimeter raised to the 6th power meters per meter cubed. In other words, we get rid of the units because those are the units of Z. And then we take the log of that to the base 10 and then multiply that by 10. So, an example, we know that the radar reflectivity factor, the radar reflectivity of a really strong thunderstorm is about 60 dBz. So if that's the case, let's find out, or let's figure out what our radar reflectivity, Z, is. Going backwards, if we say 60 dBz, divide that by 10, and then we have to take the inverse log, in other words, raise 10 to the 6th power. That gives us Z of 1 million. And there's the units, millimeters 6 per meter cubed. So that's what radar reflectivity factor is. So just to summarize, radar reflectivity factor, or dBz, is the measure of the scattering as a result of all the ice crystals in a given radar volume. And a lot of people, kind of don't really understand exactly what radar reflectivity value is. And now you do. So I hope that was enlightening.